Hello students. Topic 21 is on inverse Laplace transforms. This is the third topic in a series of 4 on using Laplace transforms to solve ODEs with initial conditions. Now the Laplace transform is invertible. For example, consider the statements below. So here we have the Laplace transform of 3e to the 2t, and that is given by 3 over s minus 2. Therefore, if I want to reverse this process, we use this notation here. This is the inverse Laplace transform. It's the L with a -1 exponent. And then you put the function of s here, and you get the original function of t. Find the inverse Laplace transform of each function below. So we're trying to recognize these Laplace transforms as something that would be in our table that we've explored in the last topic. So I'm going to toggle back to that table. And if we can somehow put these functions in a form that is one of these, then we can use this table to go backwards and figure out the inverse Laplace transform. Now the case that we're working on right now is 3 over s. Well, that looks exactly like constant over s. So the inverse Laplace transform will just be that constant. So notationally, we would say something like this. We would do inverse Laplace of 3 over s, and that just becomes 3. Or we can say the following: if capital F of s is 3 over s, then little f of t is just 3. It's a constant function. In the next case, we have 2 over s plus 3. So going back to our table, anything of the form of a number over s plus or minus another number, I'm thinking this entry of the table is going to be useful. We just have to let a be a negative number so that this would be 1 over s plus something. And then, of course, if there's a number up top other than 1, that can just be a constant multiple of the function. In other words, we can do the following. We can say that the inverse Laplace of 2 over s plus 3 is equal to 2 times the inverse Laplace of 1 over s plus 3. So the linearity of Laplace transformations also works going backwards. That doesn't look like a very good curly L. And now we can do the inverse Laplace of 1 over s plus 3. That's going to be e to the negative 3t. So we get 2e to the negative 3t. And if we wanted to call this a function of, we'll call this little g. So maybe we'll start this way. Little g of t is the inverse Laplace transformation of 2 over s plus 3. And that takes us to 2e to the negative 3t. Now in this case here, h of s is 2 over 5s plus 3. So this one's similar to the one before, except now there's a coefficient 5. What you're going to want to do is factor that coefficient 5 to the front, and you can even factor the 2 with it. So we can say that h of t, little h of t, is going to be, first I'm just adjusting capital H of s, not finding little h yet. But if we pull a 2/5 out to the side, then we have a 1 over, and this becomes s plus 3/5. Don't forget to factor the 5 out of the 3 as well. And now I can apply linearity, and also I can ignore the 2/5 and just apply the Laplace transformation to the 1 over s plus 3/5, the inverse Laplace transform, that is. And so we have little h of t will be 2/5 of, and this is another exponential, e to the, but this time negative 3/5 t. If this had been s minus 3/5, then this would have been a positive 3/5 t, because the general form is 1 over s minus a. So that means a is negative 3/5. Okay, let's go to the next slide and get some more practice. This will get progressively more complicated as we go. So in this case here, capital F of s is negative 5 over s to the 4th. So let's refer back to our table. And do you see anything here where you have a power of s in a denominator? And the one that jumps out to me is right here. We have an s to the 4th in the denominator, so you ask yourself, first of all, what's the n? So that s to the n plus 1 will really just be s to the 4th. And you deduce that n has to be 3. And so what we want is a 3 factorial up top over an s to the 4th, and that would be the Laplace transform of t cubed, t to the 3rd power. So we know that the Laplace transform of t cubed will give us 6 over s to the fourth. Well, I'm trying to do an inverse of negative 5 over s to the fourth. So I'm going to reconstruct this a little bit. I'm going to factor out the 5. I'm going to put a 6 up there where I want it to be, but then counter it with a division by 6. So I can rewrite capital F of s in the following way. It's negative 5/6 times 6 over s to the fourth. And this puts me in a position now where I can ignore the negative 5/6 and then just do the inverse Laplace of 6 over s to the fourth, and that will give me t cubed. So little f of t is going to be negative 5/6 of t cubed. And there's our inverse Laplace. The next case, we have 2 over s squared plus 25. So we have a number over s squared plus another number. So looking back at our notes, which of these looks like it would be a number over s squared plus another number? And the one that comes to mind, it's going to be one of these two. But the cosine Laplace transform has an s up top, not just a number. But the sine Laplace transform does have a number over s squared plus a number. And you want to focus on what the correct number that what's the b? If we have s squared plus 25, then b is 5. So you really need a 5 up here as well. Returning back to our notes, if I can get this so that we have a 5 up here, instead of a 2, then I would see a Laplace transform that would have corresponded to the Laplace transform of sine 5t. Well, we can factor that 2 out and put a 5 up there and counter with a 1/5. So we can say that g of s is the same thing as 2/5 of 5 over s squared plus 25. And the inverse Laplace transform of 5 over s squared plus 25 will be our sine 5t. And so little g of t will be 2/5 of the sine of 5t. This next one over here, we have 2s over s squared plus 3. Well, now there's an s up in the numerator, so that makes me think of the cosine. And the b squared is the 3, so b is going to be radical 3. And I just need an s up here. I don't need a coefficient in front of the s. So if I go back to this problem here, we can rewrite the capital H function. I can factor that 2 off to the side, so it's 2 times s over s squared plus, and that's really, you can think of that as radical 3 squared, just so you can see that the b has to be a radical 3. And so therefore h of t is going to be the 2, and then the cosine of radical 3 times t. And you can argue that these parentheses here aren't needed. Okay, let's go to the next slide. Find the inverse Laplace transform of the function below. So this one gets a little bit more complicated. We have a few functions added together. And there are a variety of ways in which we might do this. I think the best way to do this is to address them one at a time. So let's look at 5 over s plus 4 cubed. Which formula in our table has an s plus or minus a number and then with a power on it? And my eyes jump straight down to this bottom entry of the table. So our denominator, which is s plus 4 cubed, tells me that a should be negative 4 and that n should be 2, which means I should have just a 2 factorial up here. And so if a is negative 4 and t is 2, we know that, well, let's see, I want this to be a 2 up here instead of a 5. So I'm going to pull the 5 off to the front, counter with a 2 and put the 2 up there that we want. S plus 4 cubed. And this right here is the Laplace transform of e, or t squared times e to the negative 4t. Now let's just double check that real fast. We're trying to confirm that if I do the Laplace transform of t squared times e to the negative 4t, that I will in fact get 2 over s plus 4 cubed. All right, so if this is t squared, then this would be a 2 factorial, which is a 2, and this would be a cube. Right there would be a, let me zoom in. That would be a cube, and this would be a 2. And if a is negative 4, then this would look like s plus 4. So we'd have a 2 over s plus 4 cubed. 2 over s plus 4 cubed. Okay, so I feel confident about that. Let's delete this. We're prepared now to do an inverse Laplace of this part. Now for the next piece, I don't see any formulas that have a sum of involving s's and constants over an s squared plus 1. Looking back at the table, I have a case where I have a constant over s squared plus b squared and s over s squared plus b squared. But none of the formulas here have, a constant with plus or minus an s or something like that up top. So what we're going to have to do here is a little bit of algebra manipulation. I'm going to do 2 divided by s squared plus 1 plus 5 over s squared plus 1. So split the s squared plus 1 up under each part of each component of the numerator. So we have 2s over s squared plus 1 and then plus 5 over s squared plus 1. And now I can see that we have the s over s squared plus 1. That is going to take us, when I do the inverse Laplace of that, it's going to take me back to cosine t. And you can think of this as 5 times a 1, if you will, and we have a 1 over s squared plus 1. The inverse Laplace of that will take me to sine t. So now I think I'm ready to do my inverse Laplace. So that's capital F of s rewritten, and we can now go f of t. Little f of t is going to be 5 halves, and this one was t squared e to the negative 4t, and then plus 2 times, and then the inverse Laplace of s over s squared plus 1 was cosine of t, right? Because the b is a 1. Again, the b is a 1 here, and then plus 5 times, and then the inverse Laplace of 1 over s squared plus 1 is sine t. Okay, and that's our inverse Laplace. Let's go to the next slide. Find the inverse Laplace transform of each function below. All right, so now I'm starting to recognize we're at different portions of our table. We have a constant over a sum of squares, but it's an s minus 1 squared and then plus a 9. Let's see if we can see what part of the table is going to be useful. I'm thinking we're now in this area. And in one case, there's just a constant up here, and that has to be the square root of that b squared. But we can manipulate this part of it. So we're going to have to first determine what b is based off this component, and then know what needs to be up in the numerator. But the second part of our denominator is this s minus a squared. So I'm thinking that we're going to get an inverse Laplace transform that takes me to e to the at sine bt for the correct choice of a and b, and then maybe with a constant coefficient in front. All right, so this is the b squared. So I need a 3 up there, not a 2. So I'm going to factor a 2 out and counter with a 1/3 and put the 3 up there that I'm after, that I would like to see up there. S minus 1 squared plus 9. Now I can recognize that the b is 3, because there's the 3 and the 3 squared, and the a is 1. So therefore the inverse Laplace of this was capital F, so little f of t is going to be, we have the 2/3 in front, so 2/3, and then e to the at, where a was 1, so just e to the t, and then times the sine of bt, and b is 3, so sine of 3t. Okay, the next one is similar, except now I have a 2 times s minus 2. So when you see that there's an s up top, but it doesn't match, and down here is an s minus 1, then what you want to see up here should also be an s minus 1. Let's look back at our table and see why that is. When you do the Laplace transform of e to the at cosine bt, you get an s minus a both here, and here's the base of this power 2. So this and this need to match. So if I see an s minus 1 inside these parentheses, then I need this to be an s minus 1. And then, of course, the square root of the number over here will be the b. So I see an s minus 1 down there, so I need up here to be an s minus 1. And if I factor a 2 out, that should accomplish that. So that was fortuitous. And now I can see that we have the Laplace transform of e to the at cosine bt, where a is 1 and b is 3. So now I can do an inverse Laplace. We're going to get g of t next. Little g of t is going to be equal to 2 times e to the at, where a is 1, so e to the t, and then times the cosine of bt, where b is 3. Okay, now the third one in this slide is, now we've changed this to an s minus 4. So if I factor a 2 out of that, that's going to leave an s minus 2. And the s minus 2 no longer matches the s minus 1. So I won't be able to invert this as I'm if I go down this path. So let me delete this. What you're going to want to do is you're going to want to set up you're going to want to deconstruct this numerator so that we do wind up having an s minus 1 after I do some factoring. So the fact that there's a 2 here, we need to factor that 2 out. Or you can anticipate that prior to factoring the 2 out, if this was a 2 here, like we have up in the previous example, then when I factor a 2 out, I do get the s minus 1s that I'm after. So I want this to be a minus 2. I mean, currently it's a minus 4. So what we're going to do is just simply rewrite 2s minus 4 as 2s minus 2 minus 2. And now what I'm going to do is I'm going to take the first 2 terms of the numerator and put that over the denominator as one fraction, and then minus, and then do the third part of the numerator over the denominator as a second fraction. And I'm also going to do some factoring. So we have 2 times s minus 1 over s minus 1 squared plus 9. Right, that comes from this portion of our expression. And then minus a 2 over an s minus 1 squared plus 9. And I sort of brought the 2 out to the front because I need to determine what number should be up here. And that should be a 3, because this first fraction here is going to lead to a function involving the cosine, and this second one we need to prep so that it leads to a function involving the sine. So I need to put the 3 up there, but then I have to counter it with a 2/3 in front. So I've now prepped everything to do an inverse Laplace transform. So h of t, so we have the 2, and then the inverse Laplace of what I have currently highlighted is going to be e to the t cosine 3t. So we have 2 e to the t cosine 3t, and then minus 2/3 times, and then this function, when I do the inverse Laplace of it, we get to e to the t sine 3t. So minus 2/3 e to the t sine 3t. And I've accomplished finding the inverse Laplace of each of these. All right, let's go even more complicated. Find the inverse Laplace transform of each function below. Now, what we have here is we have a trinomial, s squared plus 6s plus 13, which is what you would have if you go back to your table and you actually expanded one of these 2 denominators. It would form a trinomial quadratic in terms of s. So what I have to do is I'm going to have to complete the square in order to put this into the desired form. Now the process of completing the square, if you recall, you grab the coefficient of s. First of all, you make sure there's a 1 in front of the s squared, and there is. If there wasn't, I'd have to do some factoring of numbers first. Like if there was a 2 out here in front of that, then I would want to factor a 2 out and then see what's left and then complete the square on that. But currently there's a 1 in front of that s squared, so now I can take the coefficient of s, which is 6, you divide it by 2, and you square the result. You might remember this process from completing the square in an algebra class. And it tells me that if I had a 9 right here instead of a 13, then I would have a perfect square. What we're going to do is we're going to decompose this 13 into 9 plus 4. I want that 9. So I rewrite capital F function as follows. 3 over s squared plus 6s plus 9 plus 4. So I just decomposed the 13 into 9 and 4. The 9 is what I want, because these 3 form a perfect squared trinomial, and they factor. So we're going to get capital F of s is equal to 3 over, and it factors to s plus 3 squared plus a 4. Now I'm starting to recognize what denominator we're working with. Notice there's no s's up top. There's only the s plus 3 squared plus 4 in the bottom. So that takes me to which portion of the table? The one that has a constant up top, no s's. So this is the one I want. And the a, in this case, is going to be -3, and the b is going to be 2, because there's a plus 4 right here. So b is going to be 2. So I need a 2 up here. And currently there's a 3. So I have to do a little bit of manipulation. And the fact that there's a 4 there means I must have a 2 up here, not a 3. So the next step would be, of course, to factor the 3 to the front, put a 2 up there, counter it with a 1/2, and then we have this fraction s plus 3 squared plus a 4. And now I can see if I do the inverse Laplace of this, I'm going to get e to the negative 3t, because a is negative 3, times sine of 2t, because b is 2. So now we can go, our inverse Laplace transform f of t takes us back to 3 halves e to the negative 3t sine 2t. Okay, this next one also involves completing the square, but notice also now we have an s up top, so instead of just a constant. So the fact that there's an s over an s, a linear function of s over a quadratic function of s, kind of reminds me of what we saw up here. But we still have to complete the square and then maybe break apart the linear expression and then potentially wind up with two different functions that we find the inverse Laplace of and get two functions combined. Let's see how this breaks down. So completing the square, we do the exact same process of completing the square, and I can rewrite g of s as s over s plus 3 squared plus a 4. Okay, the fact that there's an s up here means that we need to construct s plus 3, because if I'm going to use this entry of our table, again, whatever's inside these parentheses right here, it has to be the identical thing up on top. So I see that we have an s plus 3, so I need an s plus 3. And I can go ahead and insert a 0 of the form s plus 3 minus 3. So I haven't changed anything, I just added 0 effectively to the top. But now I'm going to split this up. I'm going to do s plus 3 over the s plus 3 squared plus 4, and then minus 3 over s plus 3 squared plus 4. So I'm going to break this up into two different fractions. So we have s plus 3 over s plus 3 squared plus 4, and this one's ready to do an inverse Laplace transform, and then minus a 3 over, I'm going to pull that 3 off to the front because I'm anticipating I'm going to have to do that. And the question is, what numerator does this have to have in order for me to use the sign? So let's look back at our notes. Again, if I want to do an inverse Laplace transform involving the e to the at sine bt, then whatever number is being squared here, the square root of it needs to be up in the numerator. And that's not currently the case. So the square root of this 4 right here is 2. And so we need to have a 2 up in this numerator. I need to counter it with a 1/2. Now I'm prepared to do an inverse Laplace of both this and this. So g of t is going to be, the first one involved the cosine, and the a was negative 3. So we have e to the at, so e to the negative 3t, and then cosine of bt, and b is 2. And then we have minus 3 halves, and this one involves the sign, where a is negative 3 and b is 2. So we have e to the negative 3t again, and this time sine of 2t. Okay, so completing the square was required to prep these for doing inverse Laplace transforms. Okay, we're going to get more complicated, but before we do, we're going to do a quick review on partial fraction decompositions for rational functions where the degree of the denominator is more than the degree of the numerator. And just for an aside, we're not going to actually see this in the cases of these inverse Laplace transforms, but in general, if you're doing a partial fraction decomposition, if the degree of the denominator is less than or equal to the degree of the numerator, then long division must be performed first. Now we're going to complete the table below. So this is definitely a bottom heavy. I use the word bottom heavy, if you recall, when I'm describing a rational function where the degree of the denominator is larger than the degree of the numerator. The degree of the numerator is degree 0, and the degree of the denominator is going to be degree 2. When you FOIL this, it's going to be an s squared polynomial. This is a degree 1 over a degree 3. This is a degree 3 over what would be a degree 4. So all of these examples here are, I call them bottom heavy rational functions, meaning that the degree of the denominator is more than the degree of the numerator. And that's what you have to make sure is true before you set up a partial fraction decomposition. Okay, the first rule is that the number of factors of the denominator should equal the number of fractions in the decomposition. So the number of factors in the denominator is 2. There's 2 factors here. So that tells me we should have 2 fractions in our decomposition. And you split the 2 fractions up, or the 2 factors up as separate denominators of the 2 fractions. So s minus 1 and s plus 3. And then an unknown constant will go above each of these. And I knew that really because of the next rule. The next rule says that unknown constants go above linear denominators and unknown lines go above prime quadratic denominators. So what that's saying that in this first case, this is a linear denominator. It's a degree 1, so you get a degree 0, or just an arbitrary constant up top. Not arbitrary, I should say, an it's not yet been determined constant up top. And this second denominator is first degree, so you need a 0 degree above it as well. So we have a and b that have yet to be determined, so that this fraction will be equal to this decomposition. We'll do that. We'll actually figure out a, b in a moment. Right now I'm just focused on how to set these up. And the next rule says that, or it also says that the unknown lines go above prime quadratic denominators. So using the first rule on this next example, I do see two factors in my denominator, and this one here is prime quadratic. It can only factor using imaginary numbers, and we're going to stick with the real numbers here, so we cannot factor that any further using real numbers. So that means, again, two fractions, and each fraction gets a denominator that's one of the factors of our original denominator. And now the first denominator has a line below, a first degree. So above that goes an arbitrary constant, or unknown constant, I should say. And the next one's a prime quadratic denominator. So above it goes an unknown line. So a bs plus c would be appropriate up there. And this would be the correct setup, and then we'd have to find a, b, and c. And then the last rule pertains to when there's repeated denominators. Repeated denominators should receive increasing exponents. All right, so the first thing I want to do is set up the number of fractions. How many factors are here? There's technically 3, because there's an s minus 1 times another s minus 1, and then times the s squared plus 4. So first rule says that we should have 3 fractions, because there are 3 factors. And then we just split up those factors. The s minus 1s get 2 of our denominators, and then the final denominator is the s squared plus 4. Now I do rule 2. So going in this order is important. Above s minus 1 goes an unknown constant. Above the other s minus 1 goes an unknown constant. But above the prime quadratic goes a cs plus d. And then now that I've gotten this far, now I consider doing this rule here. Do I have any repeated denominators? The answer is yes. Here's a repeated denominator. And as you repeat them, you need to increase the power. So if there was a third s minus 1, then you would have another fraction that would have an s minus 1 cubed with a constant above it. Now the reason I say you should go in this order, especially get your numerators before you do your increasing exponents, is because sometimes when you put the square on that s minus 1, and then you think about what numerator you should have, it's a temptation to put a bs plus c up there, because you see that square and you think we have a quadratic denominator. But make sure you consider what the numerator should be before you put the powers on the factors due to repetition. So before that 2 goes on that s minus 1, know that your numerator should be a constant. Okay, the final few slides all are going to involve doing a partial fraction decomposition before we can do the inverse Laplace. So in this first case, I'm going to factor this denominator. And the reason I know I have to do this was s squared minus 16. If you look back at our table, there's nothing here where I have s squared minus a number. I have s minus a number, but all the ones that have s squares have to be adding something to it. Right? Even these cases here, we have s minus a squared is adding something to it. And that's not what I currently have. I have s squared minus 4. So I'm going to have to do a decomposition of this. So this will decompose. We have 3 over, this is s minus 4 times s plus 4. And we're going to set up a decomposition here. The number of fractions will equal the number of factors. We have s minus 4 and s plus 4 as the two factors, so hence the two denominators. And then above them, they're both linear, so above them go constants, so just a and b, and we have to find a and b. Now the very next thing you should do is multiply both sides by the lowest common denominator, which is always going to be the denominator of the original fraction. And then of course we're going to take this and distribute it to both fractions, all 3 fractions involved in this equation. So that leads to the following statement. I'm going to do the cancellation as I go as well. So we're just going to get a clean 3 all alone on the left side of the equal sign. Next to the a, well, the s minus 4s are going to cancel, so we're going to have a times s plus 4. And then plus, And then next to the b, well, with the b term, the s plus 4s will cancel, leaving s minus 4. Now from here, I want to show you two basic methods for finding a and b. The first method is to pick choices of s so that some of our unknowns will cancel. In other words, if you pick s to be 4 and just plug s equals 4 into the statement, then the b will cancel. So choose x to be 4 and rewrite the statement. We get 3 is equal to, and we have a times 4 plus 4, so we have 8a, and the b is gone. So this allows me to find a rather quickly. And now I'm going to choose s to be negative 4, because that'll cancel the a but not cancel the b. And this produces the statement 3 is equal to negative 8b. So together, these tell me that a needs to be 3/8, and b needs to be negative 3/8. Okay, the other method is to take this expression and expand it and then equate coefficients. So we're going to leave the 3 on the left side alone, and I'm going to distribute the a and distribute the b, just expand everything so that there's no more parentheses. So this will be a 4a, and then we have plus a b times s minus a 4b, and then regroup according to power of s. So gather my s terms together first and factor out the s. So we have a plus b, and then that's times s, and then gather the constant terms, which is 4a minus 4b. And then you effectively equate coefficients. Now, on the left side of this equation, there is no s term, so you can think of there as being a 0s plus a 3. And then you equate the 0 and the a plus b, because those are the coefficients of s. And then you equate the 3 and the 4a minus 4b. You equate the constant terms. When you do this, you create a system of equations. We know that a plus b needs to be 0, and we also know that 4a minus 4b needs to be 3. And when you solve this equation, or solve the system of equations, you're going to get the same answers. You're going to get a equals 3/8, and b is equal to negative 3/8. So either way you do this, you find your unknown constants, and then we are ready to rewrite capital F. So this tells me that capital F can be rewritten as a over s minus 4, and a was 3/8. So we have 3/8, and then I'm going to put the 1 over s minus 4 just off to the side. So there's my a over s minus 4. I just put the 3/8 off to the front. And then we have b is negative, so I'll say minus 3/8 of 1 over s plus 4. And each of these functions are already prepped to do an inverse Laplace. This is the inverse Laplace of 1 over s minus 4. This is a 1 over s minus a situation. Right? If we look back at our table, looking at this part of my table, 1 over s minus a, when I do the inverse Laplace, I get e to the at. So we have, this is going to be an e to the 4t, and this is going to be an e to the negative 4t. So little f of t, inverse Laplace of this will be 3/8 e to the 4t, and then we have minus 3/8 e to the negative 4t. Okay, next slide. Another partial fraction decomposition will be in order. Do some factoring first. Let's factor out an s to begin. So we have a 3 in the numerator over an s times s minus 4. Decompose to some unknown over s plus some unknown over s minus 4. A pretty straightforward decomposition. Multiply both sides next by the s times s minus 4. And then simplify. And we're going to get a 3 on the left side of the equation. We're going to get an a, the s terms will cancel, so we get a times s minus 4 plus b, and then just an s next to that. I'm just going to do method 1 on this. Method 1 states pick some choices of s that'll cancel things, like s being 0 is convenient. So we get 3 is equal to negative 4a, and then let s be 4 is another convenient choice, and we get 3 is equal to 4b. So once again, we get a and b are opposites of each other, and a is going to be negative 3/4, and b is going to be positive 3/4. So now I can rewrite my g function. G of s is equal to, and we have a over s, so negative 3/4 times 1 over s, plus b, which is 3/4 times 1 over s minus 4. Now the 1 over s, what is the inverse Laplace of 1 over s? That's just the constant 1. Or if you put that negative 3/4 up in the numerator, then you have constant over s, like k over s. And the inverse Laplace of k over s is just the k. So we have g of t is equal to just that constant, negative 3/4. And then the other one here, the inverse Laplace of 1 over s minus 4 is e to the 4t. So plus 3/4 e to the 4t. And we've finished that one. Okay, let's do, we have two more it looks like. Find the inverse Laplace of the function below. We have 3 over s cubed plus s. So now we have an s cubed involved. So if I do some factoring, factor out an s, that leaves an s squared plus 4. And s squared plus 4 is prime as far as real numbers are concerned. So we want to set up a decomposition where we have a constant over s plus an unknown line, bs plus c, over this prime quadratic s squared plus 4. Now I'm going to multiply top and bottom of this equation right here by s times s squared plus 4 and see where that takes us. That gives us a 3 alone in the left. Next to the a is going to be an s squared plus 4. And then we have a bs plus c. Make sure that goes into parentheses. And then the s squares plus 4 will cancel, leaving just an s. Now method 1 doesn't get us super, it's not as convenient as it has been in other cases. Method 1 I'm talking about. And I'm just going to use method 2 on this one, which means I'm going to distribute everything on the right and then equate coefficients. So after I distribute everything on the right, we have as squared plus 4a plus bs squared plus cs. And grouping similar terms and factoring, we have a plus b times s squared plus the s term is cs, and then the constant is 4a. Now on the other side of this equation, we don't have any s's. So we have a 0s, nor do we have s squares. So we have a 0s squared. And now when I equate coefficients, the 0 and the a plus b must be the same. The 0 in front of the s must be the same thing as that c that's in front of the s. And then finally, the 3 must be equal to the 4a. So equating the coefficients gives me a system that says a plus b must be 0, c must be 0, and 4a must be 3. So a is 3/4, so b is negative 3/4. And this will satisfy all of the equations. And of course c is 0. So this allows me to rewrite capital H function as we had a over s, a is 3/4. So we have 3/4 over s if you want to write it that way. Plus, then bs, so negative 3/4 s, and the c is 0, so plus 0, and then over s squared plus 4. And we are prepped to do two inverse Laplaces. So the inverse Laplace of k over s is just going to be k. And then here we have an s over s squared plus 4. The inverse Laplace of that will be cosine of 2t. So we're going to get little h of t. The inverse Laplace will be just 3/4. And then minus 3/4 cosine of 2t. If the c had been non-zero, let's suppose that c was 5 or whatever, then you would have had a linear expression up here, and then you would have had to break it apart, much like we had to do in several of these examples up here, and especially this one here, right? When we had that linear expression, 2s plus 5 all over s squared plus 1, we had to break it up and then get a sine and a cosine out of this. So if c had been non-zero, we would have had to do something similar. But in this case, c was 0, so we didn't need to bother with that. And then finally, the last one more decomposition. We have, again, just a simple 3 in the numerator. I can factor out an s squared this time, leaving an s squared plus 4. So we have 3 different factors here. We have s, and s squared plus 4. Do not think of this as, it's better to not think of s squared as a prime factor as a quadratic factor in your denominator, because it's not prime. S squared factors to s times s. But s squared plus 4 is prime, so it gets its own denominator. So we have an s and an s as 2 separate denominators, and then we have an s squared plus 4. Now above the a And above each of these s's goes an a and a b, constants, and above the c, the s squared plus 4 goes a cs plus d. Now, don't forget the third rule. Because s repeated, put a square on the second s. And now we have a good setup. Now, it turns out that if you had thought of this as just an s squared denominator and put an as plus b above it, that you do get the exact same setup as this. But I prefer not thinking of it that way. I think of the s squared as s times s and two separate fractions. Now we get to do a multiplying both sides by the original denominator, which is s squared times s squared plus 4, and distributing it. Right, so s squared times s squared plus 4, everything's going to cancel, and then multiply here, here, and here, and do all your canceling. And so we get, in the end, just a clean 3 is equal to a times a single s times s squared plus 4, plus b, and all the s's cancel, but the s squared plus 4 is still there. And then plus, put the cs plus d in parentheses, that's important. The s squares plus 4 cancel, but the s squared does not, so that stays. And I'm going to go with method 2 on this one again. So I'm going to distribute everything. So we have as cubed plus 4as plus bs squared plus 4b plus cs cubed plus ds squared. So got rid of all the parentheses. Now gather all the s cubed terms together. So we have, there's an as cubed and a cs cubed. So a plus c times s cubed. Gather all the s squared terms together. That's going to be a b plus d times s squared. Gather all the s terms together. There's only one of them, so just plus 4as. And then gather all the constant terms together. There's only one of them. It's 4b. So now what do these coefficients have to equal? Well, there's no s squared on the left side, so we have to get a 0 out of those ones. There's no s cubed or s squared or s, so all these coefficients have to be 0. But there is a constant on the right side, so the 4b has to be the 3. And this is going to give us a system. Well, we know that 4a is 0. That's going to be the easy one to go after first. So a has to be 0. Okay, that tells me that, let's look at this first one now. A plus c has to be 0. So a plus c has to be 0. We know a is 0. So that means c has to be 0 too. Now we have 4b must be 3. There's another easy one to go after. 4b is 3, so b is 3/4. And we know that b plus d have to be 0, so that tells me that d has to be negative 3/4. And this gives me what I need. Now I'm ready to do my decomposition, rewrite my capital M of s function. It's going to be a over s, and a was 0, so that's just gone, plus b over s will be, b over s squared, so that's 3/4 over s squared, plus cs plus d. C was 0, so all we need is the d's. And that's going to be, I'll go ahead and make the subtraction, so minus 3/4 over s squared plus 4. So here's our decomposition, and now we just have to do an inverse Laplace of this. I'm going to rewrite this. On the first one, I'm going to leave the same. No, I take that back, actually. I'm going to put the 3/4 in front, and then make sure that we have the correct numerator that we need right there. So we'll come back to that in a moment. And then minus a 3/4 times, and then make sure we get the correct numerator in front of this, above this s squared plus 4. So we have something over s squared. So we got to go back to our table. Something over an s squared. So it looks like this is the one I'm going to be looking at. And I want that s to be s squared. So the n has to be a 1. So I need a 1 factorial up top. So I just need a 1 over s squared. If I had a 1 over s squared, that would tell me that the original f was just t, right? Because the n would be 1, so we would just have t here. So 1 over s squared. So that 1 we get for free. So inverse Laplace of this will be t, so let's go ahead and get that going. Little m of t is equal to 3/4 of t. So there's the first one done. And then the second one, we have an s squared plus 4 with a constant above. That is going to be looking at the sign. And we have a plus 4 there. So I need to put a 2 up in the numerator. So I need a 2 up in this numerator, which means I need to get rid of that division by 4 and make that 3/8. And so now we can say minus 3/8 of the sine of 2t. Okay, and this wraps up finding the inverse Laplace transforms and wraps up our third topic of this series of 4. The next topic will be our last topic on Laplace transforms, and it will be where we solve ODEs with initial conditions from start to finish.